Picture a vacuum. Not the machine on the closet floor, but the thing that word first meant. A pocket of pure nothing. A space swept clean of every atom, every speck, every last trace of matter. That is the picture most of us carry, and it is wrong in a way that still quietly embarrasses physics. Look hard at that supposed emptiness with the mathematics we trust the most, and the equations insist it should be flooded with energy, up to 10 to the 120th power times more than astronomers can actually find when they measure the real sky. That number has no comfortable name. It is a one followed by 120 zeros, a gap between prediction and reality so vast that the physicist Steven Weinberg called it the largest discrepancy between theory and experiment in all of science. And it grows out of the simplest idea imaginable. Nothing. The absence of things. The word you would use for a jar with the air pumped out, or for the black stretch between the stars. For most of human history, that word carried no mystery at all. A vacuum meant no air and no matter, a clean, mechanical emptiness. Take a sealed box, remove everything inside it, and whatever remained was, by definition, nothing worth talking about. It was a stage with no actors, a page with nothing written on it. Empty was just empty. Tonight, slowly, we're going to take that word apart. Before we go further, one small thing. If these quiet walks through the universe help you fall asleep, a like or a subscribe keeps the channel making more of them. You can also find us on Spotify for the nights you would rather only listen. That is the whole ask. Now, back into the dark. To understand how strange the modern vacuum has become, you have to start with how completely the old world refused to believe in it. For roughly 2,000 years, the smartest people alive were certain that true emptiness could not exist. The idea came from Aristotle, and it was stated as a kind of law of nature. Nature abhors a vacuum. Nature recoils from it, refuses it, rushes to fill it the instant it threatens to appear. Aristotle did not mean this as poetry. He meant it as physics. He argued that a genuine void, a region with absolutely nothing in it, was not merely hard to make, it was impossible. His reasoning ran through the way things move. An object falling through water moves slower than one falling through air, because water resists it more. Thin the medium, and the object speeds up. So what happens, he asked, in a medium of nothing at all, a medium with no resistance whatsoever? The object would move infinitely fast. It would cross any distance in no time, and that to Aristotle was absurd. If a true void led to an impossible result, then the void itself must be impossible. It was a clean argument and it was wrong, but its cleanness gave it staying power. For century after century, this was simply what educated people knew. Water climbed into a pump because nature would not tolerate the empty space the piston tried to leave behind. Liquid rose in a straw because the void could not be allowed to open. The horror of the void was doing the work, not pressure, not weight, a kind of cosmic reluctance built into the fabric of things. When a suction pump lifted water, the explanation was not force, it was fear. The universe pulling the water up to spare itself the offence of nothing. The trouble is that reality kept leaving small cracks in the story. The workers who dug wells and built pumps in Renaissance Italy ran into a stubborn, maddening limit. No matter how good the pump, no matter how strong the seal, water simply would not rise higher than about 33 feet. Push past that and the column broke. The water refused to climb 1 inch further. If nature truly abhorred a vacuum with an infinite dread, why did its abhorrence give out at 33 feet? Why would the universe tolerate a gap above that height, but not below it? The old law had no answer. It just stopped working, and no one could say why. Galileo himself puzzled over this near the end of his life. He noticed the limit, wrote about it, and half joked that nature's horror of the void must only extend so far, as if the fear had a ceiling built into it. He did not solve it. But he handed the problem to a younger man, a mathematician who had come to work as his assistant in the last months of his life. That man was Evangelista Torricelli, and he was about to do something no one had managed in 2,000 years. He was going to make a vacuum on purpose, understand exactly what he had made, and prove the ancient law had been backward all along. Torricelli reasoned his way toward it with a beautiful piece of guesswork. If water stopped climbing at about 33 feet, maybe the real cause was not the emptiness above, but the weight of something below. Perhaps the whole reason liquid rose in a pump at all was that the air itself had weight, and that this air pressed down on every open surface, pushing the liquid up wherever the pressure was relieved. We live, he suspected, at the bottom of an invisible ocean of air, and that ocean has heft. If that were true, then the height a liquid could reach would depend not on horror at all, but on how heavy the liquid was. Water is light, so a tall column of it could be held up. Something much heavier would balance at a much lower height. So he chose the heaviest ordinary liquid he could find. Mercury, quicksilver, about 14 times denser than water, a metal that flows, cool and bright and impossibly heavy in the hand. If air pressure was really doing the lifting, then mercury should be held up at only about 1/14 the height of water, not 33 feet, something closer to 30 inches. The experiment came together in Florence in 1643 and into 1644. Picture the setup because it is one of the quietest and most important scenes in the history of science. A glass tube, about 3 feet long, sealed at one end. Torricelli fills it to the brim with mercury, the silver metal glinting as it settles heavy against the glass. He caps the open end with a fingertip, then he turns the whole tube upside down and lowers that open end into a shallow dish, also filled with mercury, and lifts his finger away. By the old law, nothing interesting should happen. The mercury should stay put, held in place by nature's refusal to leave a gap. Instead, the column drops. The heavy metal slides down inside the tube smooth and unhurried, and then it stops. It does not empty out. It does not fall to the level of the dish. It settles, hanging there, at a height of about 30 inches above the surface of the mercury below, and above that column, in the sealed top of the tube, something opens that had never been deliberately made before. An empty space, a gap where there is no air, no mercury, no matter of any kind that could have gotten in. A sliver of genuine nothing, hovering in the glass. We still call it the Torricellian vacuum. It was the first vacuum ever created on purpose, and correctly understood, and it sat there in a Florentine tube, calmly disproving 20 centuries of certainty. Nature did not rush to fill it. Nature did nothing at all. The space simply stayed empty, and the mercury simply hung below it, and the only question left was why. Torricelli had the answer ready, and it was exactly the one the old world had refused to consider. The mercury was not held up by any dread of the void above it. It was held up from below and from outside, by the weight of the atmosphere pressing down on the open dish. All that air, miles upon miles of it stacked overhead, pushing on the exposed surface of the mercury in the dish, driving it up into the tube. The column rose until the weight of the mercury inside exactly balanced the push of the air outside, 30 inches of quicksilver, held aloft by nothing more mysterious than the sheer heft of the sky. Change the weather, and the sky would press a little harder or a little softer, and the column would rise and fall by a fraction of an inch, day by day, reading the mood of the air. He had, without quite meaning to, invented an instrument. The tube was a scale for weighing the atmosphere. When the air grew heavy, the mercury climbed. When it lightened, the mercury sank. Watch that column over days, and you are watching the pressure of the invisible ocean shift above you, an early and almost meditative measurement of a thing no one could see or feel directly. We call the device a barometer now, and we honour the man himself in the unit we still use for the very low pressures at the heart of this whole story. A torr, 1 millimetre of mercury, his name quietly stamped on the measurement of emptiness itself. But an idea this old does not die from one experiment, however elegant. Plenty of scholars looked at Torricelli's tube and simply moved the horror of the void upward. Fine, they said. Perhaps the space at the top is filled with some invisible vapour of mercury, or with a subtle essence squeezed out of the metal. Perhaps nature's dread was satisfied by something too thin to see. The vacuum could still be denied, if you wanted badly enough to deny it. What was needed was a test so clean that the weight of air was the only thing left standing. That test came from France, and from a mind that loved a decisive stroke. Blaise Pascal seized on Torricelli's idea and saw exactly how to prove it. If the mercury truly was held up by the weight of the atmosphere pressing down, then carrying the whole apparatus higher, up where less air stacked overhead, should lighten that push. And if the push lightened, the column should fall, not because nature's horror changed with altitude, which made no sense, but because there was simply less air above you the higher you climbed, and so less weight bearing down. Pascal could not make the climb himself, so in 1648 he sent his brother-in-law up a mountain in central France, the Puy de Dôme, carrying a barometer. The plan was simple and merciless. Measure the height of the mercury column at the base of the mountain. Carry the tube up the slope into the thinning air, stopping to measure along the way. Then compare. If the ancient view is right, the column should not care how high you stood. Emptiness is emptiness, and horror is horror at any altitude. But if Torricelli was right, the mercury should sink steadily as the ocean of air grew shallower overhead. Picture that climb. Cold, thinning air. A man carrying a fragile tube of quicksilver up a mountainside, stopping to read the level with care, marking it down, and with every stage of the ascent the silver column drops a little lower in the glass. By the summit, thousands of feet up, it has fallen by more than 3 inches from where it stood at the bottom. A control tube left behind at the base and watched all day never moved at all. There it was, written in metal. The mercury was reading the weight of the air and nothing else. Take away some of that weight by climbing above it, and the column obediently sank. That was the end of the horror of the void, at least as a serious idea. There was no cosmic dread holding liquids up. There was only pressure, only the plain physical weight of an atmosphere you cannot see, pressing on everything all the time, an invisible sea you have lived at the bottom of your entire life without once feeling its full mass. Water rose in a pump because air pushed it. Mercury hung at 30 inches because air balanced it, and the empty space above the column was exactly what it looked like. Empty. Nothing. A vacuum made by human hands and understood at last. For a long time after that, this was the whole meaning of the word. To make a vacuum was to remove the air, to pull out the matter, to leave behind a clean mechanical nothing. Better pumps came, and better seals, and the emptiness got emptier, closer and closer to that perfect void the ancients had sworn could never exist. A vacuum was measured by what was missing from it. Fewer atoms meant a better vacuum. 0 atoms would be a perfect one. And a perfect vacuum, everyone assumed, would simply be nothing at all, the true blank page, the stage with the lights off and every actor gone home. That assumption would stand unquestioned for the better part of 3 centuries. It felt like the safest idea in all of physics. Take everything out, and what remains is nothing, and nothing is nothing, and there is no more to say. It was only in the 20th century, when physicists learned to ask what a field does when you leave it entirely alone, that the safe idea began to come apart in their hands. Because the deeper they looked into that clean empty space Torricelli had first opened in his tube, the less empty it turned out to be. Torricelli had emptied the tube of every last atom of air, and still, 300 years later, physics would insist that the space he made was not empty at all. Torricelli had emptied the tube of every last atom of air, and still, 300 years later, physics would insist that the space he made was not empty at all. The space above the mercury was not resting, it was not still. It was humming, faintly, endlessly, in a way no barometer could ever show him. Quantum field theory says the fields that fill all of space cannot ever go perfectly quiet. Not above the mercury, not between the stars, not even with every last particle stripped away. To understand why, you have to hold one idea in your mind. It comes from Werner Heisenberg, and it is called the uncertainty principle. It says a field cannot have both an exact value and an exact rate of change at the same moment. Pin one down perfectly, and the other blurs beyond knowing. A field frozen at exactly zero, sitting perfectly still forever, would break that rule. It would have a known amount and a known motion at once. Nature does not permit it. So the field compromises, it jitters. It keeps a small, restless motion that never stops and never drains away. Physicists call it zero-point energy. It is the energy that remains after you have removed everything you possibly can. Cool the space to absolute zero. Pump out every atom of gas. Shut out every ray of light. And still the fields tremble, because perfect stillness itself is forbidden. The vacuum has a flaw. The floor is never flat. Now that trembling does something strange, the energy of the vacuum is not smooth. It flickers, moment to moment, everywhere at once, and in those flickers, particles appear. A particle and its antiparticle blink into existence together, born out of nothing, and then rush back together and vanish. They are called virtual particles. They borrow their brief lives from the vacuum, and the lone follows the same uncertainty rule. They can borrow a great deal of energy for a vanishingly short time, or a little energy for slightly longer. The only law is this: pay the debt back before the universe can measure it. Picture shrinking down to a scale far smaller than an atom, smaller than the nucleus inside it, quadrillions of times smaller than anything you have ever seen. At that depth, empty space does not look calm. It looks like a boiling sea of froth, pairs of particles winking into being and annihilating again faster than light could cross the width of a single proton. That is the ground state. That is the quietest the vacuum will ever be. It is a churning ocean that only looks like glass because you are too large and too slow to catch the waves. For a long time this sounded like a story physicists told themselves. A convenient picture with no way to check it. Then, in 1947, two men found the fingerprint. Willis Lamb and Robert Rutherford were studying hydrogen, the simplest atom there is, one proton and one electron. The reigning theory, written by Paul Dirac, said, two particular energy levels of that electron should sit at exactly the same height, identical, indistinguishable. Lamb and Rutherford measured them anyway with enormous care and found they were not identical at all. One rode above the other by a tiny amount, a splitting of 1057.862 million cycles per second. That gap should not have existed. Later that same year, Hans Bethe worked out where it came from. The electron in the hydrogen atom is not alone. It sits inside the vacuum's own restless electric field, that bath of zero-point jitter, and it is being jostled by it without pause. The jostling shifts the electron's energy by a whisper, and that whisper is the Lamb shift. It was the first hard, measured proof that the vacuum is not inert. The empty space wrapped around a single electron was reaching in and moving it. A hydrogen atom, alone in the dark, was being nudged off its true level by a field no instrument could see directly, only by the mark it left behind. 1 year after that, in 1948, a Dutch physicist named Hendrik Casimir asked a quieter question. If the vacuum's full of these flickering fields, what happens if you put a wall in their way? He imagined two flat metal plates, not charged, not magnetized, just two plain conducting plates facing each other, held very close together in a perfect vacuum. Nothing between them, nothing pulling them. Here is what he realized. The virtual photons of the vacuum come in every possible wavelength, long and short, like waves rolling across an open sea. But the narrow gap between two plates is not open sea. It is more like the water trapped between two harbour walls. Only certain wavelengths fit neatly inside. The longest waves are simply locked out because they cannot fit between the plates. So the gap holds fewer kinds of vacuum fluctuation than the open space outside it. Fewer waves inside means less energy inside, and nature always leans toward lower energy. Outside the plates, the full crowd of fluctuations presses in. Inside, the thinned crowd pushes back with less. That imbalance becomes a real force, squeezing the two plates together. Sit with what that means. Two pieces of metal in a sealed vacuum, with no charge and nothing at all between them, drift toward each other on their own. They are pushed by the difference between how much nothing exists on each side. There is no other name for the thing doing the pushing. It is the vacuum itself. Casimir gave the force a number. He predicted exactly how hard it should pull, and how that pull should grow as the plates came closer. For decades it stayed mostly a prediction, because the effect is faint and the plates must be brought almost impossibly close. Then, in 1997, Steve Lamoureux measured it properly. He used a torsion pendulum, a delicate suspended arm that twists in response to the smallest push. On it he mounted a sphere and a plate, both coated in gold, and brought them to within less than a 10,000th of an inch of each other. As they neared, the vacuum drew them together, and the pendulum turned. He measured the turn. The force matched Casimir's 50-year-old prediction to within 5%. Two mirror-smooth surfaces of gold, closer together than a hair is thick, had been pulled toward each other in total darkness by absolutely nothing you could point to. And a machine sitting on a table had felt it happen. Since then, the measurement has only sharpened. Newer experiments use atomic force microscopes and tiny etch devices to feel the Casimir force directly, again and again, always finding it exactly where the theory says it should be. The vacuum pushes. That is no longer in doubt. There is one honest argument that still runs underneath all of this, and it is worth telling you plainly. Physicists and philosophers still debate whether these virtual particles are truly real, fleeting things that briefly exist, or whether they are only a bookkeeping trick, a way of drawing diagrams and running the sums that predict the real numbers. Nobody disputes the numbers. The Lamb shift is real. The Casimir force is real and measured. What stays unsettled is what exactly is happening in the dark to produce them. The effects are solid. The story we tell about the particles behind them is still a story. That force is no longer just a laboratory curiosity. It has become a practical headache for the people who build the smallest machines we make. At scales of a few millionths of an inch, the Casimir force is no longer negligible. It is strong. Engineers who design nano-electromechanical devices, the tiny switches and levers and moving beams etched into silicon, run into it constantly. Two parts drift too close, and the vacuum draws them together and holds them. The pieces stick and they will not come apart. They have a word for it: stiction. Entire designs are now drawn to keep surfaces far enough apart that empty space does not quietly glue them shut. Sit with that for a moment. We have learned to build machines so small that we must design around the pressure of nothing. The vacuum has become a component. An engineer has to account for it the way an older engineer accounted for friction or gravity, a force with a value present whether you want it or not. So the old picture is finished. The vacuum is not a passive void waiting to be filled. It is an active medium. It is a field that hums even when you have taken everything out of it. It is a sea that jitters, that lends particles their brief lives and takes them back, that reaches in to shift an electron off its level, that leans on plates of gold in the dark and pulls them together. Torricelli's empty tube was full the whole time. He simply lacked the eyes to see how much nothing he had actually made, or how loud that nothing truly was. And this is where the ground beneath the story begins, very gently to tilt. If the vacuum carries energy, then the vacuum has a state. It sits at some particular level, its own quiet floor, the bottom of everything. And a thing that sits at a level can, at least in principle, sit at a different one. Everything we have said so far has quietly assumed that the emptiness around you is resting at the lowest level there is, the true bottom, with nowhere lower left to fall. But nothing in the Lamb shift proves that. Nothing in the Casimir force proves it either. We have shown that the vacuum can be nudged. We have shown that it can be restricted, penned in, thinned out between two walls. We have shown that it can push on solid metal and win. Go back to the spring of 1947 and look closely at a single hydrogen atom, the simplest object in all of chemistry. One proton at the centre, one electron bound around it. Nothing else. By the reigning theory of the day, this was the one-atom physicists believed they had completely solved. The equations were written 2 decades earlier by Paul Dirac, and they had been triumphant. They wove together quantum mechanics and Einstein's relativity into one elegant description of how that lone electron should behave, and that theory made a very precise promise. Inside hydrogen, there are 2 particular states the electron can occupy, 2 subtly different ways of sitting around the proton. Physicists label them the 2s 1/2 level and the 2p 1/2 level. The details of the labels do not matter to you tonight. What matters is the prediction. Dirac's mathematics said these 2 states must sit at exactly the same energy. Not close, not nearly, identical. The electron would need precisely the same amount of energy to reach either one. On paper, there was no gap between them at all and no room in the theory for one to exist. Here is the quiet engagement beat before we go deeper. If you find these old puzzles soothing, a gentle like or a subscribe helps this channel keep making them, and these scripts live on Spotify too. That is the whole ask. Now, let us return to the atom. 2 men decided to check the promise. Willis Lamb and Robert Rutherford, working in a laboratory at Columbia, set out to measure that supposedly non-existent gap directly. And they had an unusual advantage. The war had just ended, and the war had left behind a gift. To build radar, engineers had spent years learning to generate and control microwaves, invisible radio waves far shorter than the ones that carried voices. That wartime microwave technique was, in 1947, the most refined tool of its kind on Earth. Most of the world saw radar as a weapon. Lamb saw it as a ruler, a way to probe energies inside an atom with a precision no one had ever reached before. The idea was elegant in its patience. If those 2 hydrogen states really were separated by some tiny sliver of energy, then a microwave of exactly the right frequency would be able to nudge the electron from the lower one to the upper one. Feed the atoms a beam of microwaves. Slowly tune the frequency up and down. Watch for the frequency where the atoms suddenly respond, where the electrons begin to jump. That frequency, converted into energy, is the size of the gap. If Dirac was right, and the states were identical, there would be no such frequency. The atoms would stay silent at every setting. The needle would never move. The needle moved. At a frequency of about 1057 million cycles every second, the hydrogen atoms answered. The 2 states were not identical after all. They were split, separated by a whisper of energy that Dirac's beautiful equations flatly forbade. The measured value, refined with care, came to 1057.62 megahertz. Sit with how small and how exact that number is. More than 1,000 million oscillations per second, pinned down to the last decimal, describing an energy difference so faint that no one before had a tool delicate enough to notice it. The gap should not have been there, but it was, and it had a number. That is the shape of a good mystery. A theory that everyone trusted said a certain thing could not happen. Careful hands, using a brand new instrument, watched it happen anyway. The question was no longer whether the gap was real. The question was what could possibly be pushing those 2 levels apart. The answer came the same year, and it came fast. Hans Bethe was one of the sharpest calculators of his generation, and when he learned of the measurement, he chased the explanation almost immediately. The story that survives is that he worked it out roughly, quickly, on a train. The kind of back-of-the-envelope estimate that a lesser mind could not have trusted and a greater one could. His insight was to stop treating the electron as if it were alone. In Dirac's clean picture, the electron feels only the pull of the proton and nothing more. Bethe asked a stranger question. What if the electron is never truly alone, even in a perfect vacuum? What if the empty space around it is not empty? Because by then, a suspicion was already forming among physicists that so-called empty space carries a faint, ceaseless restlessness, a background flicker of electromagnetic fields that never fully settle to zero. Bethe supposed that the hydrogen electron is constantly bathed in that flicker. It is being jostled endlessly by the vacuum's own field, shaken by fluctuations too small and too fast for any instrument to catch in the act. And here is the crucial part, that jostling affects the two states by slightly different amounts. One of them is nudged a little more than the other. The endless shaking preys them apart, and the size of that gap should be, Bethe found, right around 1,000 megahertz. Think about what that means for you as you follow this. The very thing that Dirac's equation left out, the trembling of the vacuum itself, was exactly the thing that showed up in the laboratory as a real, measurable number. The electron was not being pushed off its expected energy by the proton, or by any particle you could name, or by any force in the textbook. It was being pushed by nothing, by the emptiness, by the medium we call the vacuum, which turned out to have a texture and a pressure and an effect on solid matter you could read off a dial. This is why that faint splitting in hydrogen deserves to be remembered as one of the hinge moments in physics. It was the first direct experimental fingerprint of a vacuum that is not inert, not a philosophical argument, not a clever thought experiment, a frequency measured, matched to a mechanism. Before 1947, the idea that empty space seethes with activity was a suggestion floating at the edge of theory. After 1947, it had a witness. The number 1057.62 was the vacuum leaving a mark, and the mark could not be waved away. And that single measurement did something larger than settle one puzzle about hydrogen. It lit the fuse on an entire field. In the years that followed, physicists built the theory that describes exactly how electrons, light, and the restless vacuum all weave together, the framework now called quantum electrodynamics. It became the most precisely tested theory in the history of science, agreeing with experiment to more decimal places than almost anything else humans have ever calculated. And it grew, in large part, out of the need to explain why two levels in the simplest atom refuse to line up. A tiny gap where there should have been none turned into the seed of our deepest working picture of light and matter. There is one honest thread worth leaving loose, because it runs through everything that follows. When physicists describe the vacuum jostling that electron, they often speak of virtual particles, fleeting flickers of matter that blink into being and vanish again before anything can measure them directly. Whether those virtual particles are truly real, transient objects, or only a bookkeeping trick for calculating what the vacuum does, is still argued over by physicists and philosophers alike. That debate has never been settled, and it may never be. But notice what the argument does not touch. The splitting in hydrogen is real. The 1057.862 MHz is real. The vacuum's effect on the electron is real, and it was confirmed with an instrument, whatever words you choose to wrap around the cause. So the reigning picture of a dead, empty void did not fall to a grand theory, or a bold announcement. It fell to a needle moving at the right frequency, in a room full of borrowed radar parts, tended by two patient men who trusted their ruler over their expectations. They set out to measure a gap that could not exist, found it, and in finding it discovered that the emptiness around every atom is quietly doing work. It shifts energies, it shakes electrons, it leaves numbers behind for anyone careful enough to read them. And once you have seen the vacuum nudge an electron, and later seen it push metal plates together, and restrict which waves may live in a narrow gap, the emptiness stops looking like a settled, finished thing at all. If the vacuum can be nudged, restricted, and made to push on solid metal, then the deeper question is whether the emptiness around you is truly resting at the bottom, or only balanced on a ledge above something lower. If the vacuum can be nudged, restricted, and made to push on a solid metal, then the deeper question is whether the emptiness around you is truly resting at the bottom, or only balanced on a ledge above something lower. Physicists have a name for that ledge. They call it a false vacuum. It is a state of empty space that looks perfectly stable, perfectly quiet, perfectly ordinary. It behaves like the lowest place a field could ever settle, but it may not be the lowest place at all. Picture a marble resting in a small dip near the top of a hill. The marble is still, nothing pushes it. By every local measurement, it has found its resting point. Yet just beyond the lip of that dip, the ground falls away to a valley far below. The marble is at rest, but it is not at the bottom. It is only at a bottom. That gap between a bottom and the bottom is the whole story tonight. Before we go further, a small ask. If this slow tour of empty space is helping you unwind, a like or a subscribe genuinely helps the channel drift into more feeds like yours. We're on Spotify too. If you prefer to listen in the dark, that is the only time I will ask. In the language of physics, the marble is a field and the dip is a false vacuum. The valley below is the true vacuum, the genuine lowest energy state that empty space could occupy. A false vacuum can sit undisturbed for an unimaginable span of time. But quantum mechanics does not respect walls the way a marble does. A quantum field does not have to roll up and over the lip to reach the valley beyond. It can pass straight through the barrier without ever climbing it. That trick is called quantum tunneling, and it is the same effect that lets particles slip through barriers they should not be able to cross. Here is where the calm arithmetic turns strange. If our universe is sitting in a false vacuum, then somewhere at some moment a tiny patch of space could tunnel through to the true vacuum. It would not happen everywhere at once. It would begin as a single point, a microscopic bubble, smaller than an atom, in which empty space has finally reached its real bottom. Inside that bubble, the rules would not be our rules. The fundamental constants would carry different values. The laws that hold particles together would be rewritten. It would be a pocket of a different physics born inside our own. And a bubble like that would not sit still. Nothing would hold its wall in place. The moment it formed, it would begin to grow. It would expand outward in every direction, its wall racing ahead at very nearly the speed of light. Everything the wall reached it would convert. Atoms would cease to be the atoms you know. The matter in a planet, a star, an entire galaxy would be remade as the boundary swept across it. Not shattered in the ordinary sense, not burned or crushed, rewritten at the level of what things are allowed to be. Now hold on to the detail that makes this the quietest catastrophe ever imagined. The wall of the bubble moves at almost the speed of light. Nothing in the universe moves faster than light, so no signal, no flash, no warning of any kind could ever run ahead of that wall to tell you it was coming. The announcement and the arrival are the same event. Light itself is the messenger, and the messenger travels no faster than the disaster it would describe. You would not see it approach. There would be no glow on the horizon, no tremor, no sound. The wall would reach you at the same instant the news of it could. It would pass through your body before a single nerve could carry the fact of it to your brain. Let that image settle for a moment, because it explains something about why this idea grips physicists rather than simply frightening them. A threat you cannot detect, cannot outrun, and cannot feel arriving is a threat with no drama in it at all. It is pure physics, stripped of every warning a story would normally give you. And it is exactly this featureless silence that makes vacuum decay so useful to think about. It is the cleanest possible test of what empty space is truly resting on. Describing that bubble properly asks a great deal of physics. It asks for two of our deepest theories at the same time, and it asks them to work together, which they are famously reluctant to do. The birth of the bubble is a quantum event. A field tunnels through a barrier, and only quantum field theory can describe how likely that is, or how the tiny seed of true vacuum first takes shape. That is the small scale, the world of the uncertainty principle and flickering fields. But the bubble does not stay small. It grows to swallow stars and galaxies. It sweeps across distances so vast that space itself is bent by the matter within them. At that scale, you need general relativity, Einstein's theory of gravity and curved space-time. So the full picture of vacuum decay is a rare thing. It is a single process that begins as a quantum whisper and ends as a reshaping of the cosmos. Neither theory alone can carry it. You need the physics of the very small to light the fuse, and the physics of the very large to follow the blast. That marriage is hard, and it is one reason the calculation took so long to sharpen. Sharpen it, though, they did. In 2024, physicists pulled together the most precise measurements we have of two particular numbers. One is the mass of the Higgs boson. The other is the mass of the top quark, the heaviest fundamental particle we know. These two masses, it turns out, decide almost everything about how stable our vacuum is. Feed them into the equations, and you can estimate how likely it is that a bubble of true vacuum will nucleate somewhere in the observable universe in any given year. The number they arrived at is a strange kind of comfort. The odds of vacuum decay happening anywhere in the observable universe in a given year came out at roughly 1 in 10 to the power of 868. That is a one followed by 868 zeros in the denominator. It is a number with no honest comparison in the everyday world. The universe is only about 14 billion years old, and 14 billion is a one followed by a mere 10 zeros. Against odds like 1 in 10 to the 868th, the entire age of the cosmos does not even register. On any timescale you could name, it simply will not happen tonight, and almost certainly never has, anywhere we could see. So you can breathe. The ledge, if it is a ledge, is extraordinarily wide and extraordinarily flat. Nothing is nudging us toward the edge, and yet, notice the careful word the physicists use. They do not say our vacuum is stable. They say it is probably metastable. Metastable means exactly what the marble in the dip was. Settled, quiet, at rest, but resting on a ledge above something lower rather than at the true bottom. Whether our vacuum is genuinely stable, sitting at the real bottom, or only metastable, sitting on that ledge, is not yet settled. And the reason it is not settled comes straight back to those two numbers. The verdict hangs on the exact masses of the Higgs boson and the top quark, and both of those masses still carry real experimental uncertainty. Shift the top quark's measured mass by a small amount, and the answer can slide from metastable towards stable, or the other way. We are reading the fate of empty space off the last decimal places of two of the hardest measurements in all of particle physics. That is how finely balanced the question is. The difference between a vacuum that is safe forever and a vacuum that is merely safe for now lives inside the error bars of a collider result. You might think a process theorized to end the universe could never be studied in a laboratory, and for the real cosmic version, that is true. But physicists have found a clever way around it. In April of 2026, a team at Tsinghua University in Beijing built a tabletop stand-in for the whole affair. They took a ring of ultra-cold Rydberg atoms, atoms puffed up into enormous delicate states, and cooled them to the very edge of absolute zero. They tuned the system so that its quantum mathematics matched the mathematics of cosmological false vacuum decay. Then, using a symmetry-breaking laser, they tipped their tiny artificial vacuum over the edge on purpose, and they watched it collapse. By turning the laser's strength up or down, they made their simulated false vacuum decay faster or slower, and they observed the bubbles of the new state forming and spreading over and over safely, at the scale of a speck of atoms held in light. It is a working model of a universe-ending process, small enough to sit on a bench, gentle enough to run again and again. Other groups, using ultra-cold atoms held in traps, have built related vacuum decay simulators, letting physicists study how these bubbles first nucleate, a thing that can never be watched in the real sky. What cannot be observed at the scale of the cosmos can, at last, be rehearsed in miniature. So where does that leave you, lying in the dark, resting inside a vacuum that may or may not be resting at its true bottom? It leaves you almost perfectly safe. The odds are so remote that no honest span of time makes them worth a moment's fear. The bubble, if it is even possible, is a theoretical curiosity, not a practical worry. You will not be woken by it. Nothing you love will end because of it tonight, or this year, or across the whole future history of the stars we can see. And yet the question underneath it stays open, and that is the part worth carrying with you into sleep. Our vacuum is not confirmed to be safe. It is calculated to be almost certainly undisturbed, which is a different and more honest thing. Empty space is probably sitting on a ledge, not proven to be sitting at the bottom, and the proof waits on measurements we have not yet made sharp enough. That is not a gap in the universe. It is a gap in what we have measured. But step back from the danger and look at the assumption buried in all of it, because it is stranger than the bubble. To even ask whether empty space sits on a ledge, you have to accept that empty space has a height at all. A ledge is a position. A false vacuum is a value. All night we've been treating the void as though it carries a number, an energy, a level it can rest at or fall from. Pure nothing could not do that. Pure nothing would have no ledge to sit on, and nothing lower to fall toward. The very fact that the vacuum can be false, that it can have a true bottom hidden beneath it, tells you that empty space is not blank. It is something with a setting. You cannot reach into the vacuum of the real universe and give it a shove. There is only one of it. It is everywhere at once, and it does not come with a spare. So physicists did something quietly clever instead. They built a smaller thing that obeys the same math, and they pushed on that. Consider what a team did at Tsinghua University in Beijing in April 2026. They wanted to watch false vacuum decay, the slow tip of a field out of one energy valley and down into a deeper one. In the real cosmos, that process is untouchable. It may never happen at all. If it ever did, it would happen once, spreading at the speed of light, with no one left anywhere to take notes. So they made a stand-in for it. The stand-in was a ring of atoms, not ordinary atoms, but Rydberg atoms, each one carrying a single electron pushed far out from its nucleus. That leaves the atom swollen and touchy, exquisitely sensitive to whatever its neighbours are doing. The team cooled this ring down to the very edge of absolute zero. They held it in place with lasers, a cage made of light that has no bars, and they arranged the atoms so that their shared behaviour followed the same equations that describe a field trapped in a false vacuum. That is the whole trick, stated plainly. You find a system you can actually hold in your hands. You tune it patiently until its arithmetic matches the arithmetic of the thing you cannot hold. Then the small thing becomes a kind of translator. Whatever it does, the enormous thing would do too, because both are reading from the same page of mathematics. Onto that ring they aimed a second laser, a symmetry-breaking laser. Its only job was to tilt the landscape the atoms lived on, to decide how stable their false vacuum would be. Set it gently, and the false state simply sat there, patient and quiet. Turn it up, and the false state grew restless. Somewhere along the ring a bubble of the true state would nucleate, a small region that had tipped over before the rest, and it would try to spread through everything around it. The strength of that laser was the dial. Weak, and the collapse crept. Strong, and the collapse came on fast. By turning one knob, the team could set their toy universe to fall apart slowly or quickly, and then watch it happen. They watched the bubbles form at the scale of nanometers, a few billionths of a foot across, inside a ring cold enough to be one of the stillest places on Earth. And here is the quiet luxury of the method. The real vacuum offers you exactly one silent roll of the dice, stretched across the entire age of the universe, with no replay. The ring offers as many rolls as your patience allows. Tip it over, reset it, tip it over again, change the laser, and run the whole collapse once more. A process that is meant to be a once-in-a-cosmos event becomes something you can repeat before the afternoon is out, and measure, and average, and understand. Tsinghua was not working alone in this. Other groups had been building the same kind of window for a few years already. In Physical Review A and journals like it across 2024 and 2025, teams reported vacuum decay simulators built from ultra-cold atom traps, clouds of atoms chilled and shaped until they too spoke the language of a decaying field. Their whole reason for existing is repeatability. They let researchers watch bubble nucleation over and over in a controlled way, studying the birth and growth of these bubbles in fine detail. Not one glimpse, but 1,000, of a thing that in the real sky can never be observed directly at all. None of these experiments is the cosmos, and no one pretends otherwise. A ring of a few cold atoms is not a galaxy, and the bubble that grows across it will not rewrite the laws of physics in your kitchen. What the atoms share with the universe is not their size or their stuff, it is the shape of their equations. And in this branch of physics, the shape of the equations is very nearly everything. If two systems obey the same math, they will tell the same story, even when one is a toy on a table and the other is all of existence. That principle is older than the Tsinghua ring, and it reaches beyond vacuum decay. The vacuum does more than sit in valleys, it also hums. And that hum too has been coaxed out of hiding by a system built to speak its language. Go back to Chalmers University in Sweden in 2011. The question there was a different one, and stranger. Quantum theory says the vacuum is never truly quiet, that virtual photons are always flickering in and out of it, borrowing a little energy and paying it straight back. The old dream was to catch some of those virtual photons and make them real, to turn the flicker into actual light you could point a detector at. There was a recipe for how. You take a mirror and you move it, not fast, but absurdly fast, a good fraction of the speed of light. A mirror shaken that hard cannot hand every virtual photon back in time. Some of them get left behind as real ones. That idea had a name for decades, the dynamical Casimir effect, and for decades it stayed on paper, because no mechanical mirror could ever be shaken that violently. So the Chalmers team did not use a mechanical mirror. They used a stand-in again. They built a superconducting circuit, a loop of electronics chilled until its resistance vanished, and they arranged it so that to the microwaves inside it the circuit behaved exactly like a mirror. Then, instead of physically waving a slab of metal, they changed the circuit's properties electrically, so quickly that the effective mirror appeared to jump back and forth. That electronic mirror moved at up to 1/4 of the speed of light, far faster than any real object ever could. And out of the vacuum, real photons appeared, detectable light born from nothing but the shaking of empty space. Look at what these two experiments have in common, separated by 15 years and an entire subject. Neither one poked the real vacuum. You cannot. The Swedish team could not truly wave a mirror at 1/4 of light speed, so they built a circuit that acted like one and waved that. The Beijing team could not tip the universe over the edge of its own stability, so they built a ring of cold atoms that acted like the universe and tipped that. In both cases, the move is identical. You cannot touch the thing you want to study, so you build a controllable copy that obeys the same equations, and you touch the copy instead. It is a strange kind of honesty. These physicists are not claiming to have ended a universe, or drained the vacuum. They are admitting, up front, that the real vacuum is out of reach, that it is too vast, too fragile, or too rare in its behaviour to be handled directly. And then they get around that limit not by force, but by translation. They find the same math somewhere it can be held, and they read the answer off the thing they can hold. What they keep reading over and over is the same quiet fact. The vacuum is not a blank. It has structure you can model, valleys it can rest in, a hum it never quite silences, a set of rules precise enough that a ring of atoms can act them out on a bench. You can turn a laser up and make it collapse. You can shake a circuit and make it glow. The emptiness answers every time, because it was never truly empty to begin with. It carries properties, and properties can be copied, and copies can be studied. And that is what makes the number so hard to shake off. When physicists say the vacuum has an energy, that empty space carries a value instead of a clean zero, they are not speaking loosely. They are speaking about the same structured, active nothing that the cold atoms mimic and the shaken circuit lit up. A nothing with valleys has a bottom, and a bottom sits at some height, and a height is a number. The vacuum's number is not a rounding error or a mistake waiting to be cleaned away. It is the resting level of a thing that hums and tips and answers when you push its stand in. To ask why empty space is not simply zero, then, is really to ask what sets that resting level, what holds the vacuum up at the height it sits at, rather than letting it fall to nothing. The reason the vacuum can sit on a ledge at all, the reason empty space carries a number instead of a clean zero, comes down to a single field that never switches off, not even in a perfect void. The reason the vacuum can sit on a ledge at all, the reason empty space carries a number instead of a clean zero, comes down to a single field that never switches off, not even in a perfect void. Physicists call it the Higgs field. It is not like the other fields of nature. Most fields rest at zero when nothing is there. The electromagnetic field, left alone, settles down to a flat average of nothing. The Higgs field does not do that. It holds a value everywhere, in every cubic inch of space at every moment, whether or not a single particle is nearby. That value has a size. Physicists measure it at roughly 246 GeV, a unit of energy borrowed from particle physics. You do not need to keep the number, only the strangeness of it. Even in the emptiest box you could ever build, with every atom pumped out and every stray photon chased away, the Higgs field is still there, still switched on, still carrying the same quiet value it carries at the heart of a star, or in the gap between your own two hands. So the vacuum is not a clean slate. It is soaked in something, and that something turns out to matter more than almost anything else about you. Think of the field as an invisible fluid filling all of space, one that never drains, one that presses on nothing you can feel. Particles move through it, some of them drag, some of them slip past untouched. The difference between those two cases is the difference between having weight and having none. Here is how the drag works. An electron moving through empty space is not really moving through empty space. It is moving through the Higgs field, and it feels a pull from that field the way a swimmer feels water. That pull is what we call mass. The strength of the interaction has a name, the Yukawa coupling, and it sets how strongly a given particle grips the field. A strong grip means a heavy particle. A weak grip means a light one. Electrons grip lightly. The top quark grips hard, which is why it is the heaviest particle we know, and the photon grips not at all. Light does not couple to the Higgs field. That is the whole reason a photon has no mass, and the whole reason light travels at the speed it does. The particles that carry your body, the electrons and the quarks bound up inside every proton and neutron, all grip the field and slow to a crawl beneath light speed. The photon does not grip, so it never slows. Two particles, the same empty vacuum around them, and one has weight while the other flies free forever. Sit with what that means for you. The space inside every atom in your body is mostly empty by the old definition. No stuff, no matter, just a tiny nucleus and a haze of electrons and a vast amount of gap. But that gap is not truly empty. It is threaded through by the Higgs field everywhere, without a break. And it is that threading, that constant unseen value in the so-called void, that gives the particles inside you their mass and holds them together at slow, ordinary speeds. Turn the field off, and the picture is horrifying in a quiet way. If the Higgs field dropped to zero, electrons would lose their mass, quarks would lose theirs, every massive particle you're made of would suddenly weigh nothing, and nothing that weighs nothing can move slower than light. Your atoms would not hold their shape. Matter as you know it would fly apart at the speed of light everywhere at once. The reason that does not happen, the reason you have a stable body reading these words, is a field in empty space that refuses to switch off. That is the first way the vacuum carries a value. It is a settled, working part of physics, confirmed when the Higgs boson itself was found at the Large Hadron Collider in 2012. The field is real. Its value is measured. Its job is understood. The empty space around you is doing constant silent work, and it does that work through a number stamped on the void. But there is a second way the vacuum carries a value, and this one does not go so smoothly. This is where the physics stops being settled and starts being embarrassing. Because when theorists try to add up all the energy that empty space should contain, they get an answer that is not just a little wrong. It is wrong by more than any prediction has ever been wrong before. Start from the jitter. Every quantum field, not just the Higgs, has a restless floor of zero-point energy, the faint tremor that never goes still even when all particles are gone. Each field contributes a little energy to the vacuum, so a natural question follows. If you sum the zero-point energy of every field, across every wavelength, up to the smallest scales physics can imagine, how much energy should a patch of empty space hold? The math gives an answer, and the answer is enormous. When you carry the sum all the way up to the highest energies the theory allows, the vacuum should be dense with energy, packed almost beyond imagining. Empty space, on paper, should weigh on the universe like a crushing tide. It should curve space-time so violently that the cosmos could never have grown large or old or calm enough for you to exist in it. Then you go outside and measure. The universe is expanding, and that expansion is speeding up, pushed by something astronomers call dark energy. Dark energy behaves exactly like an energy that lives in empty space itself, a value stamped on the vacuum, driving the galaxies apart, so we can measure how much energy the real vacuum contains. And the number we get is not enormous, it is tiny. It is so faint that on the scale of a single room it would be almost nothing at all. Now hold the two answers side by side. What theory predicts and what the sky actually shows. They do not agree by a little. They do not agree by a factor of 1,000 or 1,000,000 or 1,000,000,000. They disagree by a factor of roughly 10 to the power of 120. That is a one followed by 120 zeros. Try to feel the size of that gap, because a number that large slides right off the mind. Imagine the smaller value, the true one, as the width of a single atom. Then the predicted value would not be a mile wider or a country wider. It would be wider than the entire observable universe. That is the distance between what we calculate and what we find for the energy of nothing. Physicists have a blunt name for this. They call it the worst theoretical prediction in the history of physics. Its formal name is the cosmological constant problem, though many people simply call it the vacuum catastrophe. And the strange, humbling thing is that both numbers come from good physics. The prediction uses quantum field theory, which is one of the most successful frameworks ever built, tested to astonishing precision. The measurement uses careful observation of the real sky. Neither side is sloppy. They just refuse to meet. So the vacuum has the odd honour of being at once the best understood and the worst predicted thing in all of science. We know what the Higgs field is doing in it. We can trace how it gives you mass. And yet the total energy of that same empty space, the simplest possible quantity, defeats our best theory by more orders of magnitude than any error ever recorded. The nothing you were taught to ignore holds the deepest open wound in modern physics. People have tried to close the wound. One of the most hopeful ideas was supersymmetry. a proposed pairing that gives every known particle a heavier partner. If those partners existed, their contributions to the vacuum energy would partly cancel the ones we already know, pulling the prediction back toward the measured value. It was an elegant hope. But the Large Hadron Collider has searched for those partner particles at the energies where they were expected, and it has not found them. And even if supersymmetry were true in some hidden form, physicists now understand it would only shrink the discrepancy, not erase it. The gap would be smaller, it would not be gone. Other ideas circle the same problem. Some propose new forms of gravity that behave differently across vast distances. Some look for a hidden symmetry that forces the vacuum energy to cancel itself down to nearly zero. And some reach for an anthropic argument, which is less a mechanism than a shrug. It says the vacuum energy has the value it has because only in a universe with a small value could galaxies form and life arise to ask the question. In a universe with a huge predicted value, nothing could have held together, and no one would be here to notice. None of these ideas has won consensus. There is no accepted answer. The catastrophe still stands. And rather than settling, the picture is getting stranger. For a long time, the vacuum energy was assumed to be a fixed number, a true constant that has held the same value since the beginning and will hold it forever. That assumption is now being tested by a survey called DESI, the Dark Energy Spectroscopic Instrument, which maps millions of galaxies to trace how the expansion has changed across cosmic time, and its recent data, released across 2024 and 2025, show a nagging preference for a dark energy that is not fixed at all, a dark energy that has drifted in strength as the universe aged. The hint is not small. As of the second data release, the preference reaches about 4.2 sigma, a level of statistical confidence that physicists take seriously, though it has not yet crossed the 5 sigma line they demand before calling something a discovery. The second, independent effort, the Dark Energy Survey, found its own preference for evolving dark energy at about 3.2 sigma. 2 separate looks at the sky, both leaning the same way. If that hint holds up as more data arrives, it does not rescue the vacuum catastrophe. It deepens it, because a vacuum energy that shifts over time is even harder to explain than one stuck at a wrong but steady value. It would mean the energy of empty space is not a constant we have simply mismeasured. It would mean the value stamped on the void is alive, changing, tuned by something we do not yet understand. The one number we most wanted to pin down would slip further out of reach. So step back and hold both truths at once, the way you might hold 2 stones in one hand. The vacuum carries a value that works. The Higgs field never switches off, and because it does not, you have mass, and your atoms move slowly, and your body holds its shape instead of scattering at light speed. That part is a triumph, and the vacuum also carries a value that fails, an energy our best theory overshoots by 120 orders of magnitude, a mismatch with no agreed solution, and a fresh hint that it may be moving besides. That part is a mystery so large it makes the word humbling feel too gentle. Both are true of the same nothing. The same empty space that seems to hold no thing at all is at once the reason matter exists and the site of the deepest disagreement between theory and reality anyone has ever recorded. You cannot point to it. You cannot drain it. You are soaked in it right now, and it is quietly doing more than you will ever feel. Which leaves a plain thought to carry with you as the dark settles in. If even a flawless void, scrubbed of every atom, still holds a field with a value, still holds an energy we cannot account for, then the word empty has quietly lost its old meaning. There is no clean zero anywhere. There is no perfect nothing to point to. Every emptiness we can name, however deep, is really a something wearing the mask of nothing. For all its strangeness, that famous mismatch rested on one quiet assumption. The energy of the vacuum was a fixed number, enormous in theory, tiny in the sky, but steady. A single value stamped on empty space, the same yesterday, today, and 1 billion years from now. Physicists gave it a name borrowed from Einstein, the cosmological constant. The word constant was doing a great deal of work. Einstein first wrote that term into his equations in 1917. He wanted a static universe, so he added a number that pushed outward against gravity. Later, when the cosmos turned out to be expanding, he treated the term as a mistake. Then, in 1998, it came back. Two teams found that the expansion of the universe is not slowing down. It is speeding up. Something is pushing space apart and the constant returned to describe it. We call that something dark energy. For a long time, the simplest reading held. Dark energy was the energy of the vacuum itself, a constant density baked into every cubic foot of space. As the universe grows, more space appears, and more of this energy appears with it, always at the same strength. That picture is clean. It is also, quietly, the thing that made the catastrophe so sharp. You are comparing one fixed prediction against one fixed measurement, but what if the number is not fixed? What if the vacuum's energy has drifted across cosmic time, stronger once and weaker now, or the reverse? That is no longer an idle question. Since 2024, real data have started to lean that way. And if the lean holds, it does not rescue the vacuum catastrophe, it makes it worse. The data come from a survey called DESI, the Dark Energy Spectroscopic Instrument. It sits on a telescope in Arizona, and its job is almost absurdly patient. It measures the light of millions of galaxies and quasars, spread across billions of years of cosmic history. From those measurements, it maps how fast the universe was expanding at different ages. It is, in effect, reading the growth chart of everything. When DESI released its second major batch of results, the numbers did something no one ordered. They preferred a dark energy that changes, not a flat constant push, but one whose strength has shifted as the universe aged. The statistical weight of that preference reached about 4.2 sigma. In plain terms, that is a signal with roughly a 95% chance of not being a random fluke. That sounds like certainty. In physics, it is not quite. There is a line, drawn by long habit, called 5 sigma. A result only earns the word discovery when it crosses that line. So 4.2 sigma is close enough to make careful people lean forward. It is not close enough to let them announce anything. The finding sits in a strange middle place, strong enough to keep you awake, too soft to close the case. Then a second survey spoke. The Dark Energy Survey, a separate project with its own telescope and its own methods, ran its own analysis of the expanding cosmos. It too found a preference for dark energy that evolves rather than holds still. Its signal came in around 3.2 sigma. On its own, that is only a hint. But it points the same way as DESI, from a different instrument through a different pipeline. Two independent hands feeling the same shape in the dark, that is what makes physicists cautious rather than dismissive. One survey with a surprising result can be fooled by a hidden flaw in its own machinery. Two surveys, built differently, drifting toward the same answer, are harder to wave away. Yet neither has crossed the discovery line. Both could still be echoes of some subtle error shared by the way we model galaxies and their light. The honest word for where this stands is unsettled. The good news is that the universe is patient, and so are the instruments now watching it. DESI is only partway through its planned 5-year survey. Every additional year adds more galaxies, more distance, more history, and sharpens the signal or softens it. By the time it finishes, that 4.2 sigma will either firm into something solid or fade back into noise. The data itself will decide. And DESI is not alone. In space, a telescope named Euclid is now mapping the shapes and distances of billions of galaxies, charting how cosmic structure has grown. On the ground, the Vera Rubin Observatory has begun a survey that will photograph the entire southern sky, again and again for a decade, catching the faint fingerprints of dark energy across an enormous span of time. Between these three, the question of whether dark energy holds steady or drifts is being pressed harder than ever before. Within a few years, the middle place should give way to an answer. Now sit with what that answer might mean. Suppose it holds. Suppose the vacuum's energy really has changed across the life of the universe. For the catastrophe, that is not relief. It is a fresh wound. Every proposed fix for the mismatch was aimed at a single target, one number that theory had to somehow bring down to the observed value. A moving target is harder to hit than a still one. Now, the thing you're trying to explain is not just improbably small, it might also be sliding. Think about the fixes people have offered. One is supersymmetry, an elegant idea in which every known particle has a heavier partner. If those partners existed in the right way, their contributions to the vacuum energy would cancel much of the predicted excess. But the partners have not shown up. The Great Collider searches came back empty at the energies where hope ran highest. Even taken at its best, supersymmetry now only trims the discrepancy. It does not erase it. Another approach reaches into gravity itself. Perhaps gravity does not respond to vacuum energy the simple way we assume. Some theories make gravity non-local, letting it react to the average of the whole universe rather than to every jittering field at every point. In such a picture, most of the vacuum's energy would simply fail to gravitate, and the sky would stay calm despite the storm underneath. These ideas are serious. None has yet won the field. And then there is the anthropic argument, the most unsettling of the three, and in a way the most humble. It says the vacuum energy is small in our universe for no deeper reason than that we are here to notice it. Imagine a vast collection of universes, each with its own value. In most, the energy is so large that space flies apart before galaxies, stars, or observers can form. Only in the rare few where the number lands close to zero can anything wake up and ask the question. We measure a small value because a large one would have left no one to measure it. Many physicists find this deeply unsatisfying. It explains the number by refusing to explain it. None of these has consensus. Not one commands the room. They coexist as rival guesses about the same stubborn fact, and the fact has not moved for decades. Except now, perhaps, it has begun to move after all. If dark energy evolves, every one of these ideas has to answer a harder question than the one it was built for. Not only why is the vacuum's energy so small, but why does it change at all? So the picture that reaches you here is not a solved problem wearing a bow. It is an open argument, live and unfinished, running through telescopes in Arizona and Chile and above the atmosphere right now. The vacuum's energy may be a true constant, exactly as Einstein's word promised. Or it may be something that breathes, slowly, over billions of years, in a rhythm we are only beginning to sense. The theorists cannot yet tell you which. The surveys have not yet finished counting. What you can hold on to is this. Empty space carries an energy. That much is not in doubt. The accelerating sky measures it every night. What remains genuinely unknown is whether that energy is a single fixed number or a quantity in slow motion, and whether the largest wrong prediction in the history of physics is a puzzle about one value or about a moving one. The vacuum keeps its own counsel. It hums at a level we can weigh but cannot yet explain, and it may not even hold that level still. So the vacuum is never truly zero, and that leaves one last question worth carrying towards sleep. Of all the empty places that exist, from a laboratory pipe to the gulf between galaxies, how close to nothing does anything ever actually get? So the vacuum is never truly zero, and that leaves one last question worth carrying towards sleep. Of all the empty places that exist, from a laboratory pipe to the gulf between galaxies, how close to nothing does anything ever actually get? Start with the emptiest thing human hands have ever made. It sits underground near Geneva, inside the Large Hadron Collider. Around that machine runs a beam pipe, a slender tube where protons race at nearly the speed of light. For those beams to survive, the tube must be almost perfectly empty. Engineers pump it down to about 10 to the minus 13 torr. Hold that number for a moment. It is one of the lowest pressures ever built on Earth. To feel how empty that is, compare it to somewhere already famous for having nothing, the surface of the moon. The Moon has almost no atmosphere at all. At night its surface pressure sits near 10 to the minus 10 torr, and yet the collider pipe is roughly 100 times emptier than that. A tube in Switzerland, quieter than the face of the Moon. If this slow kind of wandering settles you, a like or a subscribe helps this channel keep making it, and you can find these on Spotify too. That is the whole ask tonight. Now let us keep drifting outward, away from the ground, toward the true emptiness above. Climb first to low Earth orbit. That is where the International Space Station floats, and where most satellites circle. The pressure there is around 10 to the minus 7 torr. Already that is millions of times thinner than the air pressing softly against your skin right now. To a human lung it is a hard vacuum. To the rest of the universe it is still remarkably crowded. There is more waiting to be emptied out, because empty has many depths, and orbit is only the shallow end. Leave the solar system behind. Travel out past the last planet, past the edge of the sun's reach, into the space between the stars. This is interstellar space, the dark that fills our galaxy between one star system and the next. Out here the emptiness deepens by an enormous margin. On average, interstellar space holds about 1 atom per cubic centimetre. One single atom in a volume the size of a sugar cube. Let that sit against the room you're lying in. The air around you holds roughly 10 to the 25th molecules in every cubic metre. That is 10,000 billion of them, a number too large to picture, all of it invisible and constant against your face, now empty almost all of it away. In interstellar space, that same cubic metre might hold only 1 million atoms, drifting alone, sometimes waiting years to touch another. And interstellar space is not uniform. In the hottest, most spread out regions it thins further, down toward 10,000 atoms in a cubic metre. In the cold, dark places, the great molecular clouds where new stars are born, it grows denser, up to 1 billion atoms per cubic metre. That sounds crowded by comparison. It is not. Even the thickest, heaviest molecular cloud in the galaxy is still trillions of times emptier than the ordinary room around you. The densest fog in space would be, to your body, a perfect and total vacuum. So we have gone from a tube on Earth to orbit, to the space between stars, and each step has emptied the last one out by a staggering factor. There is one deeper level still. Leave the galaxy entirely. Travel out into the space between galaxies, the intergalactic void, the largest and quietest regions in all of existence. Here the estimates reach as low as 10 to the minus 16 torr, and in some references lower still. This is very nearly a perfect vacuum of ordinary matter. Almost nothing you could name as a particle. Almost no atoms at all across distances the mind cannot hold. If you were searching for pure nothing, this is the closest that the physical universe will ever bring you. And yet even here, it is not truly empty. It never can be. You cannot pump this space clean. Because the emptiness is threaded through with things that no pump can remove. The zero-point fields are still there, humming at their lowest energy, unable to hold perfectly still. The virtual particles still flicker into being and vanish again. And according to our best cosmology, dark energy is spread through every cubic inch of it. The same faint energy of space itself that is pushing the whole universe apart. Take away every atom, every stray particle, everything you could ever call matter, and the vacuum still is not nothing. It still has a value. It still has content you cannot subtract. There is one more thing you can never escape, no matter how far you go, and it may be the strangest of all. It is a glow. Imagine you have travelled to the emptiest point in the deepest void, far from every star and galaxy and lonely atom. Look in any direction. The universe seems perfectly black, but it is not. Filling all of space, in every direction, at almost exactly the same temperature everywhere, there is a faint radiation. It is the cosmic microwave background. It is the leftover light of the Big Bang itself, released when the young universe first cooled enough to become transparent, about 380,000 years after it began. That light has been travelling ever since, stretched by the expanding universe into a soft microwave hum, and it has a temperature. The cosmic microwave background sits at 2.73 Kelvin. In the units you know, that is about 454 degrees below 0 Fahrenheit, 454.76 to be exact. It is bitterly, unimaginably cold. But it is not absolute zero. It is a little above it, and it is everywhere. Sit with what that means. There is no natural place in the entire universe that reaches absolute zero. Nowhere. Not the void between galaxies. Not the darkest gap you could ever find. Every cubic inch of space in every era is bathed in this ancient warmth, this whisper left over from the birth of everything. If you could somehow hear it, it would be the same faint hiss in every direction you turned, and the same in every place you stood. The universe cannot get perfectly cold, because it can never forget how it began. There is one exception to that rule, and it did not come from space. It came from us. Humans, in windowless rooms on Earth, have made places colder than anything nature has ever built. The coldest known natural object in the whole universe is the Boomerang Nebula, a cloud of gas expanding so fast that it has chilled itself to about 1 Kelvin, roughly 457 degrees below 0 Fahrenheit, colder than the background glow, the coldest natural place we know, and still our laboratories have gone far, far below it. In 2021, physicists working with sodium atoms cooled them to about 38 trillionths of a single degree above absolute zero. Other teams have chilled terbium atoms to around 1 billionth of a degree above it, numbers so small they barely mean anything to the senses. And every one of those experiments, for a fraction of a second, in a sealed chamber on this planet, created a spot colder than deep space itself, colder than the Boomerang Nebula, colder than the emptiest void the telescopes have ever found. The coldest places in the universe, as far as we know, are ones that people made on purpose. So that is the full ladder of emptiness, laid out end to end. A collider pipe quieter than the moon. Orbit. The space between stars with its single lonely atoms. The void between galaxies, near the edge of true nothing. And through all of it, unremovable, the humming fields, the flickering virtual pairs, the faint eternal glow, and a coldness that never quite reaches the bottom. But there is one last place left to look, not outward now, inward, down. Because so far we have been asking how few atoms a region holds. Now ask a different question. Take the emptiest patch of space you can imagine, scrubbed of every particle, and simply look closer, and closer, and closer still. Zoom past the atoms, past the nucleus, past the quarks inside the protons. Keep going down, far below anything a microscope could ever show, toward a scale called the Planck length. The Planck length is about 1.6 times 10 to the minus 35 meters. It is difficult to describe how small that is. Try this. Imagine taking a single atom and blowing it up until it was as large as the entire observable universe. Even then, after that unthinkable magnification, the Planck length would still be only about the size of a tree. That is how deep below the atom we are now looking. That is the floor of distance itself. And there is a matching floor for time. The Planck time is about 5.4 times 10 to the minus 44 seconds. It is the shortest stretch time that physics can meaningfully speak of. 1 Planck time is to a single second what 1 second is to roughly 300 million times the current age of the universe. An interval so brief that words like before and after begin to lose their footing. Now, here is what theory predicts happens down there, in the emptiest space at the smallest scale. In 1955, the physicist John Wheeler suggested that space-time itself, at the Planck scale, does not stay smooth. Not the particles in space. Space. The very fabric of it. He proposed that if you could look closely enough, the calm, flat emptiness would dissolve into something violent and restless. A froth. a boiling, flickering structure of geometry bending and warping and popping in and out of existence. He called it quantum foam. Picture it, as far as picturing is possible. Bubbles of warped space, quadrillions of times smaller than the nucleus of an atom, forming and collapsing in a single Planck time. The ground of reality seething. What looks to us like perfect, motionless emptiness would be, at that scale, the most turbulent place there is. The smoothest nothing you can name, frothing. And here is the honest part. No one has ever seen it. No experiment has been sensitive enough to confirm quantum foam or to rule it out. Building an instrument that could probe the Planck length directly is so far beyond anything we can imagine making that some physicists treat it as effectively untestable, at least for a very long time to come. Astronomers have tried indirect tests, watching for the faint blurring of light from gamma-ray bursts billions of light-years away, hoping the foam might leave a fingerprint on that ancient light. So far the answer stays out of reach, so quantum foam remains a prediction, not a sight. It sits right at the edge of what we can know. On one side, general relativity, which says space-time is smooth at every scale we have ever measured. On the other, quantum mechanics, which says it cannot stay smooth forever. And no one has a tested theory that joins the two, no confirmed answer for what the vacuum truly looks like at the very bottom. The question of what nothing is, at the smallest possible scale, is still open. It may stay open for generations. And so the journey folds back on itself. You started tonight with a simple word, empty, and the ordinary belief that empty means nothing at all. Follow it out to the collider pipe and it is fuller than the moon. Follow it to the space between the stars and there is still one atom drifting there. Follow it to the void between galaxies and there are still fields, still dark energy, still that ancient glow that will never let the cold reach zero. Follow it all the way down to the Planck scale, and the smoothness dissolves into a froth that theory insists is there and instruments cannot yet find. At every scale, near and far, large and unthinkably small, the same answer keeps returning. There is no perfect emptiness. There is no true nothing. Every void you can point to is quietly, endlessly full. Start by picturing the emptiest thing human hands have ever made. It is not aboard a spaceship. It sits underground near Geneva, inside the beam pipe of the Large Hadron Collider. Engineers pumped that pipe down to roughly 10 to the minus 10, in places 10 to the minus 11 millibar. Put plainly, they stripped away all but a whisper of gas. They had no choice. Protons race around that ring at nearly the speed of light. A single stray molecule in the way could scatter the beam and ruin the run. So the emptiness there is not a luxury. It is a requirement, engineered on purpose, atom by absent atom. Now hold that pressure in your mind and step outside all the way to the moon. You might assume the lunar surface with no air at all would be as empty as anything could be. It is not. At night the moon's surface sits near 10 to the minus 10 torr. That is a genuine natural vacuum, thinner than any sky on Earth, and yet the collider pipe beats it. The best vacuum we build down here is about 100 times emptier than the surface of the moon. Sit with that a moment. We have out-emptied the moon inside a tunnel, climb back toward Earth and stop in low orbit, where the International Space Station flies. Out there, at around 10 to the minus 7 torr, the vacuum is already millions of times thinner than the air at sea level. Astronauts float in what any old scholar would have called a perfect void. But by the standards of this ladder it is crowded. Low orbit is thousands of times denser than the collider pipe, and it is far denser still than the true dark between the stars. The higher you climb, the emptier it becomes, and the ladder is only beginning. To feel the next rung, you need a number for ordinary air. The cubic meter of it around you right now holds about 10 to the 25 molecules. Write that out, and it is a 1 followed by 25 zeros, pressing softly and constantly on your skin. Hold that count. Now travel out past the planets, past the edge of the solar wind, into interstellar space, the vast dark between the stars of our own galaxy. Out there, the average falls to about 1 atom per cubic centimetre. Imagine a single sugar cube of space holding one lonely atom. Across a whole cubic metre, that comes to roughly 10 to the 6 atoms, 1,000,000 or so, adrift in the black. It sounds like a lot until you set it beside the air in your room. Even the densest cold molecular clouds, packed near 10 to the 9 atoms per cubic metre, are trillions of times emptier than the space just in front of your face. The thinnest hot regions thin further still, down toward 10 to the 4. So picture one atom drifting for years between collisions, with nothing to strike and nothing to touch. Go further still, out beyond the galaxy itself, into the gulfs between galaxies. This is the deepest ordinary emptiness anyone has tried to measure. Estimates for the truest intergalactic void reach down toward 10 to the -16 Tor, and in some references lower. That is a near-perfect absence of ordinary matter, a stretch of nothing so complete that the collider pipe, our proudest vacuum, looks positively thick beside it. You have climbed the whole ladder of matter now from a tunnel under Geneva to the emptiest deep between galaxies, and every rung along the way was measured, not merely guessed. But emptiness has a second axis, and it is temperature. Thin out the matter and you also strip away heat, because heat is only the jostle of particles, and where there are almost no particles, there is almost nothing left to jostle. So the ladder keeps climbing, downward now, toward the cold. The coldest natural place we know of is not the deepest void. It is a small cloud of gas called the Boomerang Nebula, about 5,000 light-years away. Its temperature sits near 1 Kelvin. In the units you feel on your own skin, that is about 457.5 degrees below 0 Fahrenheit. That is colder than the general glow of space, and there is a reason. Gas is streaming out of a dying star at the nebula's heart at tremendous speed, and as that gas expands it cools, the same way the air rushing out of a can chills your hand. The Boomerang has been running its own refrigerator for centuries, and it has chilled itself below almost everything else in the sky. For a long time it held the title of the coldest known object in the entire universe. Nothing natural that we have found anywhere is colder than that quiet expanding cloud. And then, quietly, in windowless rooms on Earth, human beings beat the universe at its own game. In 2021, a team working in the Bose-Einstein condensate tradition, tied to MIT, cooled a small cloud of sodium atoms to about 38 trillionths of a degree above absolute zero. Read that number slowly. Not 38 degrees, not 38 millionths, but 38 trillionths of a single degree above the coldest temperature that can possibly exist. Other labs, cooling ytterbium atoms, have reached down near a billionth of a degree above absolute zero, both of them colder than any nebula. Set those figures against the Boomerang Nebula, and the gap is almost comic. The coldest natural place we know sits near 1 Kelvin. The coldest place humans have made sits trillions of times closer to absolute zero than that. So the emptiest, coldest spots in all of existence are not out in the deep dark at all. They're here, on this planet, built on purpose inside sealed chambers, colder than any nebula, emptier in their engineered way than the surface of the moon. We did not find the true extremes of nothing. We manufactured them ourselves. Line the whole thing up, and the ladder reads like a strange kind of poem. A tunnel under Geneva, 100 times emptier than the moon. The moon itself, airless and grey and still. Low orbit, millions of times thinner than your breath. The space between stars, 1 atom to a sugar cube. The gulf between galaxies, emptier by far again. A dying star's nebula at 1 Kelvin, a speck of sodium at 38 trillionths of a degree. Every rung has a name, and every name carries a number, and not one of them turns out to be truly empty. Because here is the quiet twist that ties the whole ladder together. Strip out every atom, every last molecule of gas. Pump a chamber down past the collider, past the intergalactic void. Cool it below the Boomerang, below the sodium, as far down as any lab can push. And something still remains, The fields are still there. The faint pressure of the quantum vacuum is still there, humming under the silence. Emptiness, measured carefully at every scale, keeps refusing to actually be empty, from the thing in the tunnel to the thing between the galaxies. So when you try to name a single truly empty place, you keep coming up short. The tunnel is full of a few stray molecules and the fields beneath them. The void between galaxies is full of that same restless energy. Even the coldest speck in the coldest lab, poised a hair above absolute zero, still quietly hums. You can walk the entire ladder, rung by careful rung, from the loudest machine on Earth to the stillest deep in the sky, and never once set your foot on solid, final, honest nothing. From the pipe at the collider to the froth predicted at the Planck length, every emptiness you can name turns out to be full of something, and that is the thought to rest on now. From the pipe at the collider to the froth predicted at the Planck length, every emptiness you can name turns out to be full of something, and that is the thought to rest on now. Let it settle slowly, the way heat leaves a room. The nothing you pictured at the beginning, clean and silent and truly empty, has quietly dissolved. In its place there is a medium, a humming, restless, energy-saturated medium. It reaches all the way down and all the way out. It is present at every scale you could ever choose to look, and it does not switch off. Trace the path back for a moment, gently, with no need to hold on to any of it. There was Torricelli in Florence tipping his tube of mercury, leaving a thin sliver of true void hovering above the metal. For a long time that sliver was the whole story, empty, meaning simply no air. Then the story deepened. The empty gap began to jitter, a fine and ceaseless tremble that no cooling could ever still. Two smooth plates, closer together than a single hair, drifted into each other, pulled by nothing you could point to, only by the difference in how much nothing lay on either side. A field ran under all of it, switched on everywhere at once, quietly handing weight to every particle that moved through it. And beyond the last atom, an ancient glow, faint and even in every direction, filling space that otherwise looks perfectly black and perfectly still. Hold the two facts side by side one last time. Physicists can calculate what empty space should contain, and they can measure what it actually contains, and the two answers miss each other by a factor beyond ordinary language. The vacuum is at once the best understood thing in physics and the worst predicted. We can name its parts, we can track its jitter, weigh its pull, watch its glow, and still the sum comes out wrong by more zeros than any mind can picture. That gap is not a flaw in your understanding. It sits, unsolved, inside the finest theories we own. Empty space is carefully measured, and it quietly refuses to be explained, and it is never at any scale actually empty. Now let that idea come closer. It is not only out there, among the collider pipes and the long cold between the stars. It is here, in this room, in the air resting warm against your skin. It is inside you. Every atom in your body is mostly space, and that space is not blank. The same field that lends distant galaxies their mass is threaded through your hands, your chest, the slow rise and fall of your breathing. The same faint tremble that nudged one lonely hydrogen atom off its note is happening right now, in every atom you are made of. You are not standing outside the strangeness, looking in through a window. You are built from it. The vacuum is not somewhere far away and cold. It is the quiet, humming ground of you. There is nothing to fear in that. The bubble that could rewrite everything is so unlikely it may as well be a story we tell ourselves to feel the true size of things. The froth at the smallest scale will keep its secret for a very long time yet. None of it asks anything of you here. You can simply let it be true. Empty space is full, gently and everywhere, and you are a small part of that fullness. That is a soft thing to carry down into sleep, not a heavy one. You do not have to solve it. You only have to rest beside it. So let your thoughts go loose. Let the numbers and the names drift out of reach, the mercury and the plates, the field and the glow, until only the feeling of them remains, a low and even hum beneath everything. You do not need to hold on to a single piece of it. The vacuum will go on humming whether you follow it or not, patient and full and quietly alive, exactly as it has since long before there was anyone to wonder about it. Let your breathing slow. Let the weight of the day grow soft and set itself down. There is nothing you must do now but rest inside a universe that is never quite empty, never quite cold, and never once, in all its vastness, truly silent. Sleep well tonight. Good night.